Hello everyone, thank you for joining my presentation. I will start my presentation with a topic, Introduction of Mechanical Stress Measurement Technology in Hydrogen Environment. My name is James Hara from Kyowa Americas Inc. I am working for Kyowa Electronic Instruments and Kyowa Americas Inc. for a total 10 years as Global Sales Application Engineer in numerous mechanical testing fields. In the last 10 years, I have provided technical support for industrial engineers with Kyowa strain gauge, pressure sensor, load cell, acceleration sensor solution, and data recording technology in numerous test applications in the world. I'm currently based out of Michigan, United States, as an application engineer to support mechanical testing and measurement work in academic and industrial institutions in North America. So Kyowa Electronic Instruments was the first manufacturer who manufactured strain gauge for the first time in Japan since 1949. And we supported mechanical testing project for automotive crash testing, component level fatigue analysis, and a transmission pipeline fatigue analysis project in hydrogen system. Our core competence is a strain gauge. Strain gauge is kind of very small device that can be applied to the material by dedicated adhesive. And we can measure mechanical deformation on our test pieces by bending, stretching, or compression. And we measure how electrical resistance will change and detect into the strain versus. It is a valuable tool for assessing the strength and the durability of the material and the structure across numerous industries. In the last decade, there's more and more demanding for stress and strain measurement for components of hydrogen energy systems. The background of this increasing demand is there are some technical challenges to overcome in adapting hydrogen for energy production system. For example, high cost and a safety concern for the material. The first point is a high cost. To safely store and handle hydrogen, we have to have a specialized equipment that can withstand the demanding conditions, including the high pressure ranging from 70 megapascal to 90 megapascal in hydrogen storage system. The material required for safely storage the hydrogen at such high pressure range are specialized and should be high cost. Robust alloys, composite, and other advanced materials are necessary to withstand the extreme conditions without any mechanical failure. The manufacturing process for these advanced materials are also complex and expensive. Another challenging point is a safety concern caused by possible material failure due to hydrogen embrittlement. Materials can weaken or deteriorate as hydrogen atoms penetrate inside the material. Because of this phenomenon, there is a significant investment for research projects in national laboratory and global laboratories for development and improvement the safety of the materials used for hydrogen energy systems. Here's a more detailed mechanism of hydrogen embrittlement. Hydrogen atom is a very small particle in nature, so it will easily penetrate inside the material. Hydrogen penetration will affect interatomic bonding of the metals. As a result, metals will be weakened and deteriorated. We call this phenomenon as hydrogen embrittlement. Here is showing how influence of the hydrogen for material strength. The graphic above is showing stress and the strain curve of the mild steel under normal air condition. The graphic below is showing influence of hydrogen for a material strength. What I want to see here is same material under same stress amount condition, material will be broken at much earlier stage due to a hydrogen embrittlement issue. In order to manage hydrogen embrittlement problem and use metal safely in a hydrogen environment, 3 steps here is really critical for quality assurance. The step number 1, measurement of material strength when it's exposed to hydrogen. Number 2, knowing the characteristic of each materials in hydrogen. Number 3 is designing and creating the materials that are durable enough for a hydrogen environment. So test engineers in the world are carrying out stress measurement by using a strain gauge durable in a hydrogen environment. Kyowa electronic instruments in Japan have developed unique and only one solution for hydrogen environment. This is a KFV model, 4-strain gauge for hydrogen gas environment. Kyowa engineering team use a special material, iron chromium alloy, for sensing portion of the strain gauge. So we could minimize electrical resistance drifting due to hydrogen embrittlement. This is a measure specification of KFV strain gauges. The specialized point is a material in a sensing portion. We use iron chromium alloy foil in a resistance element / sensing element. This type of foil is more stable in the resistance against hydrogen embrittlement. So this strain gauge is not affected by hydrogen embrittlement during measurement process. Also, our past research project revealed that this strain gauges was durable and applicable for a high pressure range up to 90 megapascal hydrogen gas exposure. This is our supporting and background data in 2013. In 2013, Kyushu University in Japan and Kyowa Electronics Japan headquarters conducted collaboration research project to reveal performance comparison of general purpose 4-strain gauge versus KFV strain gauges. We carried out measurement of strain gauge output under no load condition in 90 megapascal hydrogen gas. As a result, we found KFV strain gauges has much more been effective and stable against hydrogen effect exposure. The red value here is the KFV strain gauges. The drifting range is within 250 micrometer per meter strain over 20 hours. On the other hand, general purpose strain gauges is showing more significant amount of drifting over 20 hours, which is due to effect of the hydrogen embrittlement in the sensing portion. This performance comparison and difference is due to advantageous point of iron chromium alloy, which is used for a sensing element of the KFV strain gauges. The point number one is a lower amount of saturated hydrogen in iron chromium alloy. It contributes to electrical less resistance and gauge factor change due to high pressure hydrogen. Advantageous point number two is a higher hydrogen diffusion coefficient in iron chromium alloy. It contributes to faster electrical resistance stabilization in the hydrogen environment. These two advantageous points is coming from a cubic structure difference between iron chromium alloy and a copper nickel and nickel chromium alloy that are typically used for general purpose 4-strain gauge. When you look at the iron chromium alloy, it is more body-centered cubic structure. This geometry of body-centered cubic structure will provide more pathways for hydrogen to diffuse more easily. On the other hand, when you look at the copper nickel and nickel chromium alloy foil, typically used for general purpose 4-strain gauges, it has a more face-centered cubic structure. This more densely packed geometry have more atomic packing factor or confining factor compared to the body-centered cubic structure. So more hydrogen atoms will be trapped and get stuck in the cubic structure, which causes more hydrogen embrittlement in the gauge sensing element in the end. Because of a superior performance in KFV strain gauges, this KFV solution has been used for development of hydrogen storage tank material analysis and also a transmission pipeline material analysis. The one example is an investigation of the tank material behavior for H2 storage application. Conventional strain gauge in the market has shown more significant drifting amount due to a hydrogen embrittlement, so they couldn't do an accurate strain measurement. So they switched to a KFV strain gauges made by iron chromium alloy, and they could achieve more stable and accurate measurement for their future products developments. And also, measurement capability in 90 megapascal high pressure range supported their fatigue analysis process in their real pressurized environment. And the second case study is a comparison of fatigue life of the materials in load testers under normal air condition in hydrogen environment. Kyowa provide not only KFV strain gauge, but also tension and compression type load cell and clip type displacement transducers. Those specialized transducers help them expand their research opportunities. So we, Kyowa, have offered more comprehensive measurement solution from strain gauge, signal transducer to data recording system in hydrogen environment. One example is a compression and a load cell, compression and tension type load cell that is typically used for load cyclic testing and fatigue analysis on the material. And also creep type displacement transducer. This is typically used for crack propagation testing and a material. That's all of my presentation. Thank you so much for your attention to my presentation. If you want to more detail about the technology and a company introduction, feel free to visit our booth number B54. Thank you so much. Yeah, so I'm really open for any kind of questions. So if you have any question, feel free to let me know.